Manufacturing and industrial environments provide their own unique challenges for wireless communications. Harsh conditions, both indoors and out, create a daunting task for engineers to work through. This is where we come to discuss those challenges, share ideas, and help one another out. My name is Scott McNeil, and welcome to the Industrial Wi-Fi Shop. Welcome back, everybody, to the Industrial Wi-Fi Shop. My name is Scott McNeil, and I'm excited today because I have my very good friend Jim Palmer with me, and we are going to talk about a lot of great stuff. Jim, could you tell everybody a little bit about yourself, please?
Hi, everybody. My name is Jim Palmer. I am a Wi-Fi person at Ruckus. I tell people all the time I have an official title. I've forgotten what that is. A long time ago. I just know it's like 5 words, and I don't know what any of it means. I'm just like, yeah, I'm a Wi-Fi person at Ruckus Ruckus Networks, and in a bigger perspective, and we've been talking about this over the past hour and 20 minutes before we hit record. Um, I I am at heart. I'm actually a radio guy. I started with radios back in 1993 with the U.S. Army, and I've just been doing radios ever since. And about 12 years ago, 12, 13 years ago now, I started dabbling in Wi-Fi a little bit because I got bored we ran out of projects at the job I was working at. And they're like, hey, go take the Wi-Fi guy around and show him around the place I was working because it's massive, right? Our campus was 53 square miles, and so yeah, so they're like, can you go show the new Wi-Fi guy around because he's got to go find all the Wi-Fi stuff, and it's 53 square miles. So I was helping this guy out, and I came back to my boss, and I was like, look, I don't know anything about Wi-Fi. But neither does this guy. And I was like, and worse, I was like, he doesn't even understand radio. I was like, so this is going to be a bad, bad time. And sure enough, it was. And so we finished a project and we were bored. I was bored. I was super bored. I wanted a new challenge. And so they had me helping the Wi-Fi guy more and more and more. And I was like, man, I was like, we have to change something. And so I ended up taking over his job, and the rest, is you can say, is history. So I,
Nice.
with that background, I think this is what we're going to talk about. And have been talking about that history sort of brings me into the Wi-Fi space from a whole different aspect and place, because I started with radio. And so the one thing that most Wi-Fi people struggle with, that RF, the actual RF, is the one thing I do understand. I get that part. For the longest time, I thought a layer 3 was a little thing you carried in your pocket. And I didn't know what a layer 3 was. Literally thought it was like a little token, like a little like VPN token. You set to punch in your code to get your password out of. We were in a meeting one time, and I told them they were arguing over who had the layer 3. It was the firewall manager and the network manager. And they were like, you have the layer 3. I have the layer 3. And I said, somebody ought to figure out who has the layer 3 so you don't take it home in your pants pocket and wash it. I was like, maybe put it in a drawer somewhere so we can find it. And they kind of looked at me like, what? What are you talking about? And I'm like, and so I like held it up. I held up this little thing, and I'm like, well, it's the layer 3 is like this, right? And for those of you who's can't see on this audio only podcast, I'm holding up a flash drive. And I was like, it's like this, right? And they're like, no, you moron. And I'm like, I'm a radio guy. I don't know this stuff. So there you go.
Well, one of the reasons I asked Jim to come and talk with us today was to talk just about that, was to talk about all things RF, radio frequency, um, and all the things that can affect RF in your environment. And being that this is the industrial Wi-Fi shop, we always talk about the differences between enterprise and the industrial manufacturing landscape. So when you're looking at an enterprise environment, we're talking about things that are very, very common that everybody has in their offices. It's that cause attenuation on RF, and that's cubicles, walls, elevators, different things like that. But that's all enterprise caliber stuff. It's a completely different universe when you're walking the factory floor because you're not having to worry about ceiling tiles. You're not having to worry about uh, cubicles or Joe's office chair. It's a little bit different. Um, and your common interferers are different too. What are you seeing interference wise, enterprise side?
You know, it's funny because you use the word common a lot,
I
right?
do.
So, well, and but you do for a reason. Let's just admit it, right? From a Wi-Fi perspective, when we talk about like common things, it's so common and it's so, dare I say, boring that it's boring,
It
right?
is. It's incredibly boring. When
So,
I transitioned from higher ed into the industrial universe, my job became so much more exciting, and because the challenges that exist here just don't exist in enterprise.
well, I took the Ekahau planning, the Ekahau planning software long years and years ago. I took their ECSE class, and I took that from a gentleman named Fernay Munoz. And I took CWDP, the design professional course, from Keith Parsons. And now these two gentlemen have taught probably more design classes than the rest of the planet combined. Um, they've done it more than most of the people on the planet. And so it was funny to watch them do these classes because they would put up a floor plan of like, and it was one of their common floor plans, but they could draw and design the network in seconds almost because they had done it so often. So what those guys bring with that experience is because everything is so common, they can look at a standard floor plan from an enterprise environment and they just go, oh, this is going to be a problem, this is going to be a problem, because they just have that experience because it's so common. It's common for a reason. And so, yeah, what you find a lot of time in enterprise has nothing, what's common about enterprise is that it's all the same. The interferers are all the same. Microwave ovens. That's a prime example. We had an alert one time in one of my jobs, and it was actually weird because it wasn't my network. The place where I worked actually had 5 enterprise Wi-Fi networks operating in the same place at the same time, and so
There's no congestion there.
yeah, none. Just Scott, you know this, but people who don't know me wouldn't know this. But I can talk about it now. Is I actually worked at Denver International Airport for 12 years, and so one of the airlines came to me and they're like, "Hey, we're seeing this alert on our Wi-Fi system for a microwave oven interfering," and they're like, we went through and we looked and we didn't find any brand new microwave ovens that had been put in, and I was like, well, that's not where that alert's coming from. I was like, it's not a brand new oven. I was like, brand new ovens are shielded. I was like,
Right.
what you're looking
Exactly.
for is a really old oven.
Microwave
It's
oven.
it's been there forever and it looks like, it's something you don't really want to put your lunch in, but you do anyway. I was like, so that's what you need to go find. And so that's where, from an enterprise perspective, that's what makes it uncommon is like you have these things. But then we also see stuff like IoT, light controllers and all these other things. And it all lends itself. And I think this is something that most people don't understand is like the 2.4 gigahertz band, which is very common. And I have to imagine, I haven't done as much industrial as you, but I have to imagine that's really common in industrials 2.4 for
Very.
Wi-Fi perspective. Um, but the 2.4 band, is the ISM band. So if you don't know, ISM is industrial and scientific something, right?
Right.
So, so, but now why is it the 2.4 band and why do we call it industrial and scientific? Because by happy accident, 2.4 gigahertz is the best frequency in which to boil water. Now, microwave ovens work by boiling water. They heat up the water molecules in your food, and that's what reheats your food. So that was discovered by accident by a guy who melted a chocolate bar in his pocket. And he was like, "Why did my chocolate bar in my pocket melt?" And it come to find out. Well, so here's the problem, right? So microwave ovens or science ovens came about because they could boil water more effectively at 2.4. And what they figured out was the earlier shielding on these microwave ovens was utter garbage. And so what they realized is the 2.4 band with all these new science ovens that have been people were putting out and using all over the place was really bad for communications. And so they said we can't sell that spectrum, right? We can't sell it because no one's going to pay us for that spectrum because it's just flooded with the science ovens. And we're afraid about this. And so that's why Wi-Fi 2.4 exists in that band, is because they couldn't sell the frequency. They couldn't sell that spectrum. Nobody would bid on it. No one would pay for it. So they're like, well, it's free. Nobody, well, what are we going to do with it? Well, let's take all this industrial and scientific and all these other type of weird use cases that are never really going to go into production. And let's just make that spectrum free. And so when Wi-Fi was looking for a free spectrum, they said, hey, look, we can use 2.4. So anyway, way off on that tangent.
I learned something new every day. I didn't realize that's where that came about.
That never happens talking to me, is when you're getting off on a tangent. But anyway, so that's where that comes from, right? And so again, it gets boring because that's just how it is. But the same thing happens, I believe, in industrial, because now you can walk into a space and you can be like, you might not know exactly what it is, but you can look at a big giant machine and go, ooh, I want to know more about that one, because
That one right
that
there,
one,
because that's a likely culprit of
it's
producing some kind of interference.
so even if they don't have a problem, you can look at it and you can say, oh, and so it's common, and so that's why that's where the experience comes in, right? That's where, it's like, I don't remember if this was before or after we hit record. I was like, I know the mistakes that people are going to make because I've already made them. I've already been burned by it.
Right.
I've already gone there. I've spent hours walking around, and you've spent hours walking around a facility trying to figure out what something is, and then you come out and you go, oh, it's that machine. And so then you learn about that machine, and then when you go to the next customer and you walk in, you're like, ooh, that machine looks a lot like that other machine
That other machine, that other site.
I was at last month. Can
Yeah.
we talk about that machine? Because I want to know about that. Even before there's a problem, you're just like, ooh, because in your head, in your eye, you see that and you're like, ooh. So it's like, again, and that's why I think what makes what especially Wi-Fi is kind of interesting, is because you can do that transition. People are like, I can do an enterprise space in no time flat because I already kind of know what's going to happen. I know elevator shafts, I know, bathrooms, I know, they're gonna put in IoT controllers, they're gonna put in light controllers. How often do you see that on social media where, so it just becomes common and boring. And so with Wi-Fi, with what you've discovered, going from, hey, I'm going to start working in an industrial thing, it's all about the challenge. It's all about, and that's what I was talking about when I got into Wi-Fi, because I got bored. It's
Right.
I'm like, I got done building an air to ground radio system, which had a really cool, had a voter system built into it, which was, a voter system is, you have multiple receivers staggered all over your airport property, and the audio, airplane transmits. There were three receivers. We had three receivers set up, staggered all over the complex. They would take that audio, send it via fiber back to a box that would then compare the different audio levels from the different receivers, and it would pick it and be like, this is the best audio I want. It would take that audio, and then that is the audio that would pump up to the controller sitting in the tower, and that's what they would hear. They would receive it three times. And so this is an old MIMO trick, right? From like 11N days. This is what they figured out in 11N, and radio's been doing it for a lot longer than that. Is we're going to receive the signal, from different antennas. In an AP, we have different. You remember the old diversity receives?
Yes.
That's what that did, right? Is the
Okay.
diversity receive would be like, I get one signal on one antenna, another signal on another antenna. I'm going to take a look at it. I'm going to pick the best one.
Right.
Two-way radio's been doing that for decades, right? And so that's what we do, is we pump that audio. And so we got done with that project. It was really cool. Got to build a 7-foot tall rack that was 4 feet deep, filled with cavity filters, and we would tune them. Took me 2 days to tune that thing. Best 2 days of my life. So, um, so that's the cool thing about Wi-Fi and radio is there's so many different applications. There's so many different ways you move around. So you get to that point where you're like, ooh, now I want to go learn about something else. And you just change, hey, you still do Wi-Fi, but I'm going to do it in a new place. I'm going to learn about what are these common interferers? What are the common things I find? Oh, I know that the wall here, by building code is always going to be different.
Right.
So then I know that the attenuation value of that wall is different. You know, People who do hotels, same thing. They learn, oh, they like to do cool things in the bathroom. So when I see a plan where the bathrooms are next to the hallway, I know I'm going to have problems.
Yep.
And so it gets to that point where you find weird things, and the weird things are always the things that don't fit the common mold. And so that's what we love to sit around at the bar and in podcasts and things like this. And we tell war stories about, hey, this one time,
Exactly.
you know,
Exactly.
I and let's be honest, who doesn't like to sit around and tell war stories?
Yeah, that's fun, especially over a good cold beer. You know,
Exactly.
and it's interesting too when you look at your interferers, and but it's not just machinery that's doing it. It's non-Wi-Fi based interference, because there's a lot of protocols in the industrial sector, in the 802.15.4, that we've talked a lot about 2.4, that they're all in 2.4. When you're looking at wireless HART, when you're looking at ISA 100, these are frequency hoppers, and they're in 2.4. They're not in 5 gig. So you take that 2.4 that already has all these problems, because of everything else that's going on. Now they've also got some frequency crowding, because a lot of these industrial IoT protocols all use frequency hopping in that space as well. And it's interesting because a lot of drives, the large electrical boxes that essentially control motors, if they're not shielded properly, they're actually called VFD, variable frequency drives. If that doesn't give it
Mhm.
away, nothing does, right? And then if they're not shielded properly, they will kick out a ton of EMI. And for those not familiar, EMI is electrical magnetic interference.
Electromagnetic interference.
Easy
And
for me to say.
yeah, and here's the thing, right? When we talk about non-Wi-Fi interference, we end up talking a lot of times people just think of a modulated signal, right? And we go because even though you deal in a lot more stuff nowadays than I do in a lot of different bands, we're still talking about a modulated signal that somebody designed to do, right? Whether it's a frequency hopper, whether it's IoT, whether it's whatever, it's a device that's been designed to transmit at a specific frequency or maybe hop frequencies. I mean, there's a design concept behind there. Somebody sat down, some engineer sat down, used to be with a pencil and a slide ruler, and now it's all computer based. But they sat down and they said, we're going to design something that does X. And I would argue that those are actually pretty simple to figure out because somebody at some point bought and installed those, right? And so it's easy to figure out because you're like, oh, well, you just have to ask the right question at the right time to the right person. And all of a sudden they're like, oh, yeah, Joe over in HVAC just bought these new HVAC controllers because they're trying to get more of this. Or, oh, we just brought in this new machine and we can monitor it and it wirelessly and it talks to this other part of the line is doing another thing and they now communicate, or you're doing BACnet or all these other things. There's all these other protocols, but somebody designed it and then somebody from the company bought and installed it.
Right.
But I want to talk about EMI because EMI is something that we I think a lot of times we just kind of glance over. We're like, oh yeah, EMI. And then we wave our hands and we go, EMI. It's kind of like, remember back in the day when it was cloud and
Yes, you just
it's
said
in the
cloud.
cloud and somebody they're waving their hands, and it's like,
Right. Can't you just put it in the cloud?
but
You
it's
put that
in
in the
the
cloud, please.
well, we do the same thing with EMI, right? But EMI is a much more difficult thing to figure out because
Completely.
it's not something that was bought and installed to do something specifically. So nobody buys EMI. Nobody 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 buys a product because of EMI. It's be like,
Right. Yeah. No, nobody goes
like
to Cisco and say, "Hey,
it's
can I get the new EMI 5000, please?"
exactly. Nobody does that. So trying to figure that out. But here's the thing, right? And this is what makes it interesting is because we were talking about this in the first hour of the podcast that wasn't recorded. Is there's this natural harmonic in things. There's this natural thing. And so you have these variable frequency drives. And so the frequency thing makes a thing. But at the same time, it's also, we talk about like even just power, right? Let's talk about the power that we use to power our houses or power data centers or power stuff like that, right? In the US, we use 110 volts. which but there's this other little thing in there that we sometimes gloss over a little bit, which is either is it 50 or 60 hertz. Well, that's a frequency, right?
Right.
And then you have data centers which are running 240, and oddly enough aircraft run at 400. um there's a bunch of physics and other math behind it that explains that. But mainly you can use smaller gauge wires because 400 hertz, you can get more amperage over it on a smaller gauge wire. In an aircraft, weight makes a lot of impact, so they run a higher power so that they can do all. So they have to actually, when you plug in your phone into an airplane seat now, you have to actually down convert from 400 down to
So you don't fry your phone.
yeah, exactly. So anyway, but we're still creating frequencies, and so these motors that are taking in that power still create frequency. And even when we have intentional radiators, there's still this power of or the problem of power. I tell a story. One of my favorite stories is we had a 2.4 gigahertz Wi-Fi access point that we could sit sit 60, 70 feet away from this directional patch antenna that was pointing directly at us. And we could see the beacons at like neg 50, right? Great Wi-Fi signal. And we would go to connect to the SSID, and we would get this terrible connection. And so we ended up with a tool, and we said, hey, show us what BSSID I'm connected to when I connect to this SSID. And it turned out we were connecting to the APs that were way on either side of us, to the left or right, like hundreds of feet away. So we got on the tool. We said, we want to connect to that AP right there, that BSSID. Make me connect to and only connect to that guy. And it failed. It never failed. It never worked, never worked, never worked. To make a long story short, what we figured out was that a cell company had put up some new LTE stuff at 700 megahertz. And it was about 60 feet behind our AP.
So
And
you got some what? That's about a second step harmonic. Is that what that is? Or is it third step?
it wasn't harmonics. It was power. It was the actual power. If you guys do industrial, you've done industrial. Have you ever gone into a place where they needed so much power they have their own like electric room?
Oh, yeah, that's called an MCC. Absolutely.
Okay. And
Most of the places I go actually have their own power generation plants.
and have you ever walked into those and you get this weird feeling in your chest?
Yeah, that's usually just before an arc flash takes you out.
So, do you want to see a big power generating building, plant, place? Go to what's known as a runway lighting vault that runs all the lights on a runway. Those things, you can't spend too much time in there because your body starts to vibrate. Like your whole body will vibrate. It's odd. It's really, but it's cool, right? It's super cool. But anyway, it's all about the power, right? You get enough power that you can feel it in your body, right? That power, just no matter the spectrum, no matter the intentional radiated frequency, and we think about a spectrum analyzer and we see these nice little clean waves a lot of times, right? Well,
Right.
we're fooled in this, and you know this if you played with an actual spec an, you know, it's not clean. It's not, there's always little artifacts, there's always little things.
Right.
You get enough, and if you get enough power being generated close enough to you, you can actually see the noise floor jump on a
Yes.
spec an. You've seen this, right?
Absolutely. Yes.
So now imagine an intentional radiator who's making, but it's intentional at 700 megahertz, but the power is so high that the noise floor just bounces like 20 dB.
That's incredible.
So think about that, right? So
Yeah.
if you add 20 dB to your noise floor and you have a little device sitting 60, 70 feet away from the AP, even though you can get enough signal there, the noise floor is actually raised up so high that the AP can't decode it because just the whole spec across the entire spectrum, the noise floor is so high because you're just, again, it's not on the spectrum. It's not on the channel. It's not it's an intentional radiator and not even and gigahertz away from where you are. But if you get enough power, and that's what's fun about industrial stuff is it's like you can have a machine that is taking so much power, right? That they have their own power plant, that they have to do all these cool things with power, but it's still running at a frequency. But the power level and the way it raises the noise floor is so high that they can't, there's no signal to noise ratio left anymore in that signal, so no one can hear it. So they can hear it, they just don't understand it because
Right.
I explain it as going to you go to a rock concert, you go stand up in front of the speakers stack because you want to hear it the loudest you can, and you get there and you realize this sounds like crap. And Hamina did a post on this a couple of weeks ago on LinkedIn where they were talking about, if you get an AP and you put it too close to a wall or to a window, it drastically changes how that RF behaves
It
around those
does.
things.
It absolutely
And
does.
and I made a comment and I said, this is what I talk about when I say I want my AP to breathe. I want to have my AP far enough away from things, from everything, that we get outside of this window of being so close that it just jams everything up, and it lets the electromagnetic waves, sort of breathe. It's like being like right up next to the wave generator, whether it's a wave pool or your concert. You need to get away from the source of that a little bit and just let those waves kind of do their thing for a little bit, and then let nature take over. And then when you get outside of that initial couple really high peaks and valleys, then it starts to work a lot better. And so, again, it's the same thing with your power things, except you're now dealing with these massive EMI generators, whether they were intentional or not, and it's usually unintentional. Um, and you want to get away from that. And you've learned this. You might not know this is what you're doing, but this is what you're
Right.
doing. You're like, we got to get away from it. It's the same thing we talk about when we measure wall attenuation. You don't put your AP right up next to the wall you're measuring. You
No.
want to get it away. You want to let that thing breathe.
You want
You
to let
want to
that
let those
signal you want to let that signal propagate out and actually get a
and
chance to go where it's supposed to
and
go.
kind of let nature take over, take its course for a little bit. Then we come in. That's why I always laugh when people are like, "Well, I put my laptop 2 feet away from my AP," and I'm like, "Oh God."
This is kind of a great segue. We've been talking about commonalities and how things become common. And on the industrial side, one of the things that has become common to me is uh, antenna misplacement, and as far as where it has been installed, how it has been installed. And a big thing that I see at many sites is people love to put high gain omnis right smack up against large concrete steel reinforced pillars. And they have no idea how that actually warps the signature of what that antenna is supposed to be propagating out. They just think it's magic, and then it's going to have it's supposed to stick out like this, and everything's going to be covered and everything's going to be fine, but they have not taken into consideration what's happening up against that reinforced pillar of concrete, let alone what else is going on around it, and the fact that they're trying to cover an area that's 30 feet below that antenna with something that's very high gain.
You know, and it's funny, we talked about this in the first hour. Um, Maybe we should have recorded that for
I
episode
think we probably
part.
should have, now that the hindsight being 2020.
So it's funny because, again, it's one of those things where, and we were talking about this in relationship to parabolic dish antennas. And you put in a 1 meter parabolic dish for 900 megahertz. And there was some misunderstanding we won't get into, but
Thank you. I appreciate that.
I'm here for you. So the parabolic dish, right? Let's go to something that most people understand, most people know about, is like a direct TV dish or a dish antenna, that you get for a dish TV that you put on your house. Have you ever really looked at one of those? What you'll notice is the actual dish itself, the big thing that collects snow and wind, is actually just a chunk of metal. That's all it is. It's just a chunk of metal. And when you look at the coax cable that runs, from your house, the installer has that coax that comes out the bottom of it. If you ever really trace that thing, it actually goes up that arm that's sticking out away from the dish, and it goes out to the element. So the coax actually plugs into the element that's at the end of the arm. And if you really look at it, that that stuff is actually pointing to the dish, right? Because that chunk of metal is simply just a reflector. And so, while a concrete reinforced concrete pillar, however you want to say it, is not an intentional designed, reflector dish. the concept is still the same. We have a massive chunk of metal, you know, that we're putting stuff right up next to each other. So it's going to turn it into a reflector. You know, that's how you want to make an omnidirectional antenna directional, put it next to, and I've seen some in there's a product from Motorola. I don't even know if it's still around anymore. It's called a Motorola Canopy, and it's used a lot in wireless
Oh, I
ISPs.
used to, yep, I used
And
to see Canopy around a
and
lot back in the day.
and they had the normal one, right? You just put up the little rectangle thing on the top of your house, and
Yep.
it point to a central point. But if you needed a little extra distance, what they do is they take that thing, they'd flip it, and they take an old TV dish, and they would point it, and they'd point the thing at the dish, and then it would turn around and reflect it back. And so that's how they do it. You want to make an omnidirectional antenna directional, simply take a reflector and put it next to an omni. Now you got to play with the spacing a little bit so that the reflector is the right length away from the directional. And this is what happens when we talk about Yagi antennas. Again, from hour one that you missed, everybody else missed. On a Yagi antenna, it's the second element from the mounting point, from the base. It's the second element is the driven element. And so that is what defines the frequency. And they make it directional by adding that piece that's between the base end and the where you're pointing your Yagi. They make that thing bigger. And so that then turns it into a directional. Is by simply just adding that little piece, and it's all spaced according to the maths. And they do all the math. Somebody smarter than us does the math and says, hey, this is the length I need that element. This is the spacing I need that element. And then I can turn it from an omni, because the driven element, if you look at a Yagi antenna, the driven element is simply an omnidirectional element that has other things built around it to make it directional. So yeah, same thing with your high gain omni thing. And we won't even get into what that actually does to the signal. I actually did a project one time where we were looking at doing we're doing directional antennas. That was the original idea, because we were like, hey, we're shooting a signal down a tunnel, right? It's an
Right.
actual, a square tunnel. And I was like, and I'm like, so of course I just want to shoot it down the tunnel, right? I know exactly where I want, I have a fixed point in the tunnel. I want to cover this point down here. And then I was like, wait, I need to cover the point down the other side. So I need to get two back-to-back directional antennas. And I went, wait a second, that's going to double my cost. What if I just went with a high gain omni? I was like, I could do it with one, but the high gain omni is really just a patch antenna that goes out in all the directions. And so I was able to actually cut my hardware count in half and my installation cost in half by simply going, well, instead of using two back-to-back patches, I'm going to use a single high gain omni and simplify the process. And it actually worked out a lot better doing it that way.
Now, in that shooting down the tunnel, did you have a problem with the radio stepping on itself, or was there too much reflection?
So that actually you're a little prophetic on this one, because it turned out that we were getting about 1,600 yards out of a single AP.
1,600 yards out of a single access point.
We were having we put in we put in the proof of concept, right? And they were like, and the people that requested that we do this, they came back and we were running real-time video over this, right? And they came back and they go, it gets kind of choppy, right? They're like, it gets kind of choppy when we get to this point, and we're like, that makes no sense, right? Well, so this leads to a story where I spent, so again, this was at Denver International, and if you've ever been there, there's a single train that connects everything together. And if that train breaks, so does the entire airport. But anyway, that's in the news. You can go Google it. Uh, um, and the train just makes it, and it just runs down a single track that's like miles long, right? And so I ended up standing in the train in front of a camera with all these sheets of paper, and I was literally like flipping my sheets of paper to tell the people watching the feed where I was. And what we figured out was we were actually an entire concourse further away from our proof of concept section of the track than they actually thought they were. So they were like, oh, we thought it was bad at B. And we're like, no, we don't get bad until C. But we have 3 APs between them. We just hadn't turned them on yet. So then
Wow.
it was, so it was like, so then we had to go back and redo a whole bunch of stuff because we were like, it's working so much better than we ever intended.
That is insane. That is
Yeah.
absolutely insane.
But it's one of those things. And this, you know, we're talking about debate, beam width and gain and stuff like that. And I think there's a really simple common concept in radio that I think, and it took me a long time to learn this, so don't feel bad, right? Especially if you're just starting out. Because again, I've been doing this for 30 some odd year. What year is it? It's 2024.
2024.
So I've been doing this for well over 30 years at this point. Um, there is a very direct relationship between the gain of an antenna and the beam width because we create energy, right? This goes back to the whole, energy or matter is neither, created or lost. It just ends up being transferred, right? We transfer it into heat, we transfer it into energy or torque or something. We're just converting it, right? So we generate RF and we then manipulate that RF and when we increase the gain, we have to lose something somewhere. And that's in the beam width, right? So the higher the gain, the tighter we get those beam widths windows. Think about it as you have a building and it has this massive single window, right? So you can see all kinds of stuff. But it's like, but if we wanted to if we wanted to increase that, we end up having to shrink the window down, which means now, because we're increasing like the magnification of that, we then end up with, we lose something somewhere. We don't get anything for free. And so when
Right.
we increase the gain, we decrease our beam width, whether it's a horizontal or vertical beam width. We have to lose it somewhere. And that's, I think, what people sort of lose track of is we cannot, you can't have a high gain and a high omni in the same thing. It doesn't work. The
Yeah.
physics, the physics prevent us from doing that.
I and I think a lot of it too is part of the culture of bigger, better, faster, more, right? You see, we want more power. Oh, and you get you just want to, oh, well, wouldn't the 9 dB Omni be better than the 3 dB Omni? Because it's got more power. Well, and this is where you
It
have the
doesn't.
trade-off,
It
you know?
doesn't have more power.
Well, I understand, but it has more gain.
It has more gain.
It's amplifying that transmit power, is it
It
not?
is not. It is not
Ah,
amplifying.
correct me, oh wise one.
It doesn't amplify it because we're not running, there's not an active element on our antenna elements. There's not power going to that. When I was doing my two-way radio stuff, and especially around public safety, the radios that the cops and the fire department use and stuff like that, we used to put what was known as a tower top amplifier in place. So we'd actually run AC power up a tower and we would put an active element, something that was using electricity at the antenna, and that would be our amplifier. What we do with antennas add what's known as passive gain. So what we're doing is we're just manipulating the shape and the energy that is sent to the antenna. We're not amplifying it in any way. What we're doing is we're shaping it. And
Okay.
it's kind of like when you compress something, you compress coal enough, what happens? It turns into a diamond, right? When you start to compress these things, something else happens. Now we never compress RF to the point that it turns into a diamond, but I can change this to something else that's a little similar. If you compress light enough, you can cut with it.
That's
You have a
true.
laser. You have a laser. You've
Right.
compressed the light. You've compressed it enough. You've actually changed the properties of, and light is an electromagnetic wave. So in RF, we never get to that point. At least I actually have a sign outside my office door that freaks out visitors that come to my house that says the RF radiation fields beyond this point exceed human standards, and so you can't enter without wearing a radiation monitor. X-ray machines. MRI machines. We take those waves and we make them high enough power that they actually do other things that we can then utilize on the other side to help with medicine. Um, RF, all we're doing is just simply we're taking the energy that we get from our transmitters, and when we talk about especially industrial stuff where we're using an external antenna, you know, and this is the class that I teach at WLPC. Really, we actually cover this when we play with this using gear that most Wi-Fi people have never even seen or touched and played with. And so it's really fun. We get to play with RF. And what we do is we get to see what happens because you have free space path loss. That's a common thing, right?
Right.
Free space path loss dictates that for every 2 meters, we lose half the power or something, right? And it's a given thing. Free space path loss. We actually have cable path loss. And so different types of cable. And this is why I like the cable for your car battery that goes from the car battery to your starter is this really thick cable, right?
Right.
But if you've ever changed a car stereo, it's a really thin power cable because we're not running as much power across it. And so if you increase the dimension of the cable, the gauge, right? This is where Cat 6A and Cat 6 and Cat 5 differ. We need higher power for our 802.11be APs. So we need 802.3 BT power, which is 60 watts of power. You have to have a thicker gauge. So Cat 6A and some of the higher category cables will be like a 22 gauge. And if you've ever put your own RJ45 connector on, you know the difference between a 24, a 23, and a 22. Well, it's a thicker gauge wire because we need to run more power across it. Coax cables are the same thing. People talk all the time. They're like, oh, I'm using LMR 400 because it's low loss. And I'm like, yeah. When I installed the radio system at the Mandalay Bay, it's a little hotel down in Vegas, Las Vegas. It's on the Strip. You might have heard of it.
Heard of that.
It's a little hotel.
Little tiny one. Yeah.
Little tiny one.
They play cards there.
I installed their two-way radio system before it was opened. I was running 1 5/8 inch cable through that hotel.
Wow.
So you want to talk low loss?
That's low loss.
Yeah. LMR 400 is like what? It's a little less than half an inch.
Right. About your thumb, roughly.
We're talking about something that the center conductor is actually hollow in that cable because the RF doesn't go down the center of it. It rides down the skin of the center conductor. The center conductor is hollow enough you can put your finger into it.
Wow.
So you terminate that cable. There's a thing is about 2 to 3 inches long, about this. It was literally about the size of your finger, and you would screw it into the center conductor.
Holy cow!
That became the center pin of the connector.
Wow.
So anyway, you want to have low loss. You have a bigger diameter, right?
Right.
And so it's the same concept. And so we but we have loss in that. And each connector gives us about a quarter dB of loss. So if you have one cable with two connectors, right, you automatically have a half a dB of loss just in the connectors alone. And that's a good high quality connector. A bad connector will give you half a dB of loss per connector. So if you have a crap cable, you already have like 1 dB of loss just by having those little connectors that you screw on. And I have all my stuff packed for WLPC, so I can't show off to people who can't see anything.
Well, then one of the back to the common things we see. One of the common things I do see is when these installs are done outside. Many times it's inexperienced hands in industrial, and so those LMR connections, as they're being connected to their antennas, are not sealed. And first rainstorm or two that comes through, that LMR gets loaded with water, and all their transmissions goes to just crap.
So what do we call people in Wi-Fi? We're big bags of water.
That's true. People are big bags of water.
People are big bags of water.
Big bags of water.
And so so that when we talk about stadium Wi-Fi or arenas or auditorium, we always say it's really hard because as soon as you fill it with people, there's so much attenuation. So now think about taking the attenuation you get from a big bag of water, and we're literally going to put it in between, because on any type of connector, right? You have the pin and you have the socket. You have the male and the female.
Right.
We might have to put this as a PG-13 rated podcast now. So even there's it's a simple, it's a compression fitting, right? The pin inserts into these little, and if you ever really take one of those things apart, what you realize is it's basically four pieces, that are sort of pushed together, but you can spring those things apart. If you want to have fun, take one of those connectors and take a screwdriver and shove it right down the middle. Take like a flat blade screwdriver or a big Phillips or whatever and shove it straight down in the middle of that connector and it'll spread out into four pins.
Yep.
So it's just a compression fitting that keeps the pin, the center pin conductor, onto the jack. And so here's the thing: water can get between there because that compression fitting is not watertight. So if you get water into the cable, it actually sits. So what you have is you're now adding attenuation, literally in the middle of the conductor. If you've ever done fiber optic cable, it'll be like, hey, let me put a piece of paper between in the middle of my fiber optic connector. Guess what's going to happen? It's never going to work.
Not going to work.
So that's where water comes from. Water is just an attenuator. Everything is an antenna. I tell people this in my class, right? Water will conduct electricity, right?
Right.
Drop a toaster in the bathtub. Not that I'm recommending that, but anyway. But
I think we're going to have to crank this up to a PG-13.
But it's not a great conductor, right? You need a lot of power because the path loss is really high, right? Think about that. The path loss of water, even though it conducts, it's not a great conductor. I'd much rather have a piece of copper because copper is a great conductor of these electromagnetic signals. So it's a great conductor. Water will work, but it's not great because you lose a lot in the process, right? But when we talk about getting like struck by lightning, there's just so much power, 1.21 gigawatts.
Exactly.
I mean, there's just so much power that it can overcome that loss in the path. And this is something that I think, even if we shift from external antennas to internal antennas, traces on a circuit board have loss. Everything has loss.
Everything has loss.
Everything has loss. It's just a matter of how much loss. And so,
if you can predict that loss from the beginning, that allows you to have a successful deployment because you've already taken that into consideration.
And that's where the EIRP values come from.
Okay.
Think about it. EIRP, for those who don't know, is effective isotropic radiated power, right? So we have the thing that generates our power, our radios, our APs, and we set those. We set those in the settings, right? You go into your controller and you say, I want to transmit at, power level 1. I want to transmit at 20 dBm. I want to transmit at,
18 milliwatts, whatever.
18, whatever, right? You set those values, but that's what is coming out. There's always, it's that moment of inception, right? There's always that moment where it's right there, but we then start losing from that exact moment until, it's a loss until you get to something like an amplifier, like we were talking about earlier, which then takes that signal and then amplifies it. Now, the other problem with an amplifier is it amplifies your signal and the noise. So keep that in mind. A lot of times in radio, we'll have an amplifier, and then immediately after that amplifier, we'll have a bandpass filter, which so we have to then filter. So we amplify it, and then we run it through a filter, which then induces loss, but it knocks out all the noise, and we just take a little bit of loss on it's called insertion loss. We take a little bit of loss on the signal that goes into it. So what comes out is a little bit less than what comes out of the amplifier, but it's now a much cleaner signal because we've run it through a filter. So there's always these trade-offs, right? And then of course, if you have a little power supply that goes nonlinear and it creates EMI, then you now are introducing EMI into your RF, which we go back to before. So there's all these little things that happen, right? We get nothing for free. And so you have the loss, and the connectors, the coax, you always have those loss. So then what you do is if you can and we can calculate the loss really simple. In my class I teach, we actually use an inline watt meter, and no one's ever done it, but I give them a little 3-foot chunk of coax, and that's our test coax. But I also bring a 50-foot piece of coax, and I'm like,
now, is this standard RG6? Like what's in your house?
So RG6 is 75 ohm, and you can't use it.
Okay.
You have to use RG8. That's 50 ohm. 75 ohm changes the impedance and it screws up all kinds of radio stuff. So don't ever use 75 ohm stuff. But 75 ohm stuff happens to work real well because it's between the radio signal impedance and the television signal impedance.
Mm.
Television signals they run best at 300 ohms. So 75 is a nice trade-off because of the harmonic stuff of how of all the impedance part works. We won't get into impedance. So anyway,
That's a whole nother show.
whole other show. But so I think I use LMR 200, so it's half the size of LMR 400, but it's a much longer chunk, and so you can actually see we know how much power comes out of the radio because we set it at 1 watt. It's the lowest I can get that radio to go. Any lower, it actually starts screwing with the oscillators, and they don't oscillate on frequency; they'll drift a lot. So when we talk about minimum powers in stuff, it's actually to protect the oscillators because the oscillators need at least it's kind of like if your car is running on really bad gas. If you've ever gotten bad gas, you don't have a high enough octane in the gas and your engine runs like crap.
It's terrible, and you use up twice as
The,
much fuel.
the same thing happens with radio. If you're not getting a good enough signal, if you're not asking the engine to perform well and you perform to the bare minimum, it doesn't run very well, and the frequencies will drift off of the center frequency because even though we have 20 megahertz wide or even 25 kilohertz, or in two-way radio we're down ICOM D-Star, which is a digital ham radio protocol, runs at 6.25 kilohertz wide channel bandwidth.
Wow.
Yeah. So anyway, we still have that channel bandwidth, right?
Yeah.
Old radars were the only thing that were really close to, they would only use the center frequency. They'd send out a small pulse. Because it wasn't very wide, it was really hard to jam, right? So you always got a clean return on your signal. Modern radars aren't like that. There's actually other modulated signals anyway. So what'll happen is if you turn the radio down too low, the center frequency will drift. And so you're still talking about, we'll use a 20 megahertz wide Wi-Fi channel, right? It still has that center frequency, and then we're 10 megahertz above or 10 megahertz below. But if that center frequency drifts, we move to the right a little bit, right? If you think about a channel chart that shows 1, 2, 3, 4, 5, all of a sudden now we're running like channel 1.5.
Right.
And if your receiver is listening for channel 1 and it gets channel 1.5, is that the intended signal or is that adjacent channel interference?
To me, that would appear to be adjacent channel interference.
So then it works like crap. So
yeah.
So anyway, it's a long way of saying that we want to generate some energy, and it's got to be up to a certain level. And then we know how much we can measure, how much loss we know what we're generating. We know what we're getting out on the other side. So that is our loss within the antenna transmission system, whether it's a millimeter trace on a circuit board or a 20-foot piece of LMR 400. We know what the loss is. So at that point, we know we need to get back to where our effective isotropic radiated power is. We take our transmitted power minus the loss through the transmission line and all the connectors and all the other loss that we have. Then you get the power that reaches the antenna. So now we know what our loss is. Then you can raise the gain of your antenna. And so that's where we have the difference. So if you ever wonder why we have a difference between transmitted power and EIRP, right? Because especially in 6 gigahertz, and well, even 5 gigahertz, we standardize on EIRP. We go, hey, there's a 36 dBm EIRP value we cannot bust. We cannot go above 36 dBm EIRP. We can't do it. That's against the law, right?
Right.
And that's so we don't cause interference outside of it. But you calculate that number because then you take EIRP calculates in the antenna gain value. And we use dB because it's a simple mathematical formula, right? We have plus 20 dB. We lose 6 dB. So now we're down to a plus 14 dB. And if we want to get back up to a plus 20 dB EIRP, we need to add 6 dB of gain. And so the gain of your antenna offsets the loss in the cable. But because it's not an active amplifier element, then the signal ends up getting manipulated to get that 6 dB of gain back into the signal level so that we're actually transmitting at 20 dBm EIRP. So that value means we've taken our loss of the system between the thing that generated the signal and the thing that's radiating the signal. We've accounted for that loss, and then we've added that gain back in, and then you can go higher, but you still can't bust 36 dBm EIRP.
And then once all of that gets to the antenna, it's that
Yes.
gain that then affects
Yes.
antenna gain that then affects the shape of the signal that's then coming out of it.
Yes, because again, we're not actively doing anything to it. We're just simply shaping it. We're manipulating it, but we're not amplifying it. We're not, and so the only thing that we can effectively do without running AC power. Think about what would if I went to you and said, "Hey Scott, you can still use external antennas, but you have to run AC power to each one of them." You would shoot me.
Yeah.
You you'd be
Yeah.
like, no, Jim, you can go take a flying leap because I ain't doing it. And you'd be right. You'd be right. So we're not doing that and so what we're left with is this passive gain and this passive manipulation of the signal to try to get it back to that level that we need. But and so understanding how that changes it um is and you understand how it changes it by reading the antenna charts. And antenna charts in and of themselves are really fun because they're hard to read because
They are hard to read, and
yeah,
not every antenna supplier gives you those charts with the antennas.
and well, they should. You can go find it because they will publish it, but they won't always be packaged in. I've known people that they'll go find the antenna chart, they'll print it out, they'll cut the antenna chart out, and then they'll laminate it to the antenna so that they have the chart on it. So for like their test gear and their test rigs, they know what the pattern is. But I discovered something really kind of interesting, which nobody will know because even the people that I asked didn't know this. You cannot make a blank antenna chart. The tools that they use to generate the antenna charts, you can't make one without a signal.
Interesting.
The modern tools that they use, that the antenna manufacturers use, do not allow you to generate an antenna chart that doesn't have a signal on it. So I wanted one for my class because I was like, I want to teach you how to read the chart, right? Because we always have to find like the 0 degree point. We have to look at the concentric circles that are in the chart. We need to take a look at all these different things. And so I have some buddies of
The
mine.
different axes represent and whatnot. Yeah.
Yeah. So I was like, and what I realized, what I learned in having some conversation with some really smart people is that we lack a fundamental understanding of how to read just the chart without the signal on it, right? Too many times we've seen an antenna chart and it has this signal on it. Now, that's because it turns out they can't make a chart without a signal. They have to put a signal because the tool won't make a blank chart. I asked him, I said, I want a blank chart that I can put up for my students and be like, let's talk about the chart itself without the signal. So we're not distracted by looking at all the the colorful lines and all the different machinations and all the little ways they go and everything. And no one can see me waving my arms around like a fool. But anyway, um,
For those who've never really looked at one of these radiation charts, imagine an amoeba on a piece of paper in a circular grid with a target crosshairs going through the center, and that amoeba has its weird splotchular kind of outline to it, is kind of similar to what you would see with certain antennas.
So yeah, so it turns out you can't actually make a blank one. So they came back to me like 2 days later and they're like, it's not great. They're like, but it turns out we can't make these charts without a signal. They're like, so we had to, they're like, they did me a solid and they manually built one for me, but it's not round because to get all those round curves, you need to have 360-degree points of reading, which they get when they put the antenna into a chamber. They get those 360-degree points. So, so that's why the charts are nice and rounded, is because they have 360 data points, which just happens to be, a circle. It's So they
Well,
have 300, and so they're able to map it, and then it makes all the things round. So mine's like this weird, weird shape, has like 16 sides because they did me a solid, and they're like, how? Because they'd never tried it before. Um,
well, so
and
at
so
this point, I think that's when we need to engage someone who's really good at Photoshop, who can take a pre-existing and then, just take the
it's
lines of the existing uh stuff right out of it.
but the one thing that always messes people up that we'll talk about real quick, because we can talk about this without having a picture, is the antenna charts are built in degrees. So like 1 degree, 2 degrees, 15, 30, 90, degrees like you'd have on a compass, right? Everybody gets that. Everybody understands that. So that's the outside of your circle, right? Ooh, your outside of your circle is basically degrees on a compass. And what we have, but then within those are some concentric circles that just get smaller as you go towards the center, right?
Right.
It's like a target, like you were talking about with the target, right? You see a target, and it's like the outer rings give you less points, and the inner rings give you more points, kind of like a dartboard, right? Same idea. These rings are spaced in there, and the rings represent dB, not dBm. dBm is decibels in relation to milliwatts, which is a representation of power. dB is just decibels. It has nothing to do with milliwatts or power. So when you look at it and it shows it as being 5 dB down, 10 dB down, or even 5 dB up, it'll be a plus, right, for a gain antenna.
Right.
So there's because the antenna designers don't know exactly how much power you're going to put into it. They can't tell you how much power you're going to get on the other end because they don't know the milliwatts going in. They don't know that power. So the charts have nothing. And people always ask me, well, so on a directional antenna, that's that point, right, at top dead center, right at the 0 degrees, which is directly off the face and the front of the end of a directional antenna or a Yagi, right? We use Yagis. They always ask me, they're like, so how much power is there? How much milliwatts is there? And I'm like, they don't know because they don't know how much is being put into it. That's a dB representation. And so when you say I have a 9 dB gain or a 9 dBi, which is dBs in relationship to an isotropic radiator, isotropic radiators is a perfect antenna. It does not exist. You can't build one. So it's a theoretical concept of a perfect antenna and everything. And so dBi means it is decibels in relationship to an isotropic radiator, a perfect isotropic radiator, which does not exist. It's a theoretical mathematical problem. So when we talk about a 9 dBi gain, that's where you have to do your dBm calculations of I got 12 dBm into my antenna plus a 9 dBi gain, which means I'm now adding 9 dB to my 12 dBm, which then gives me an effective isotropic radiated power of 21 dBm. But we can't, because we have loss between our measuring tools that measure the wireless signal, we can't actually, there's not a cable that plugs from the other end of your antenna into the measuring tool, right? There's no
Right.
cables on the other end. We don't have the cable on the business end. I heard a guy once, he called that the pointy end. He's, he's like, that's the pointy end. When we were, tell you a story. We were doing when we were installing the Mandalay Bay system. It was a five at the time. I have to imagine they've upgraded in the past 20 some odd years. It was a 5 channel 100 watt. So each channel was 100 watts, right? And we were still installing it, and we hadn't fully cabled it up yet. But the radio shop that we worked out of was close enough to the Mandalay Bay that they could hit the tower. They could hit the antenna on the roof of the Mandalay Bay from our shop. And they wanted to find out where we were. And the only way to talk to the inside of the Mandalay Bay was using two-way radios because it wasn't done yet, right? But the whole thing's built out of concrete. And we were in this concrete room. So they're like, hey, they're working on the radio system. Let's talk to them over their brand new radio system. Except when they keyed up, they ended up getting assigned to a channel that wasn't fully connected yet. There's a thing called the control channel, and then you have your operating channel. And so the operating channel worked fine because we connected that one yet. They got assigned to an operating channel we haven't finished cabling yet. And so it was this half inch hard line. So half inch around, solid copper jacketed outside shield, right? And a
Wow.
solid center conductor. It's not braided. There's no braid in any of this. It's all solid copper. And it wasn't connected up yet. And so 100 watts came shooting out the end of that cable in the form of a blue flame about 6 inches long. And I saw an old fat white guy like me climb up the inside corner of a cinder block wall, screaming like a little girl because there was flame shooting out the end of the cable. Again, energy. Energy is neither
Oof.
created nor destroyed. We just transferred it. So the energy from the 100 watts coming out the end of that cable was transmitted into converted into a blue flame. And so that was scary.
I'd have been
And
crying like a little girl too.
oh yeah, no, and RF energy is a different kind of energy as we've, if you ever wondered, like when people ask you, hey, does RF, is Wi-Fi going to cause cancer? Well, no, but I will tell you that a blue RF flame shooting out of a cable is not something. It's kind of like a torch. You're like, you're like, I don't know exactly how bad this is going to hurt if I stick my hand in front of a torch,
Right?
but how about we just don't ever find out?
Right. Well, a lot of people are amazed when you tell them that, your microwave oven uses 2.4. It's the same thing you use in Wi-Fi, only it's got a whole lot more power behind it and it cooks your food. So while it might not give you cancer, it it can certainly cook you if you're not careful.
Well, think about it, right? Um, when you if you ever read the instructions on how to cook your burrito, right? Have you ever done that? Or you just throw your burrito in the
Now,
microwave?
I wrap it in a paper towel, toss that sucker in there, hit 60 seconds, and check it.
But if you read the instructions on your frozen burrito, there'll be actually different times, right?
Different
Based
time for
on
different elevations usually, and different power microwaves.
different and what are those power microwaves represented in? How do they categorize the power of the microwave oven?
I would have to go look at a burrito.
It's in it's in watts. Is it a 900 watt,
Well, that's true. Or a
1000,
900 to or 1,000 to a
1000
watt.
or 1100, or it's a watt, right? So you worry about your Wi-Fi doing 2.4 at
Milliwatts.
zero point 0.1 watts, and yet in your kitchen you have your science oven that's doing 2.4 at 1,000 watts, right? It's the exact same technology. There is no difference in this technology. It's an electromagnetic wave that just so happens to resonate at the same frequency that water resonates at, which then boils water. So that's where the science oven comes from, boys and girls.
So for the past hour, you have gotten the most in-depth explanation of boiling water that you ever thought you may have gotten. Thank you. Good night. Have a great day.
That's what this podcast is about, right? How to boil water.
How to boil water. Absolutely.
This is a cooking show, boys and girls.
Yeah, Jim, I want to thank you for taking time to come and hang out with us. For a parting shot, do you have any words of wisdom for those OT guys down the trenches who may not know very much about antennas in general, on some basic rules of what to look for when choosing the proper antenna for a project?
So I'm gonna. I do not have a silver bullet because it just doesn't exist, right? RF is such a unique and fascinating topic and subject. I mean, keep in mind, we're an hour into the recorded aspect of this podcast, but Scott and I have been talking nonstop about this stuff for 2.5 hours at this point, and we're still having to cut it short. So if you look at RF and you say, hey, I don't understand it. I don't know it. I want to leave you with a couple of quotes. We'll start with some quotes real quick. And
Fantastic.
it's from a guy whose name is Heinrich Rudolf Hertz. Now, Hertz, when we talk about megahertz, gigahertz, was all named after this guy. He is the guy who proved James Clerk Maxwell's theory of electromagnetic waves in 1864, right? So think about who we're talking about now. And he also said I'm not sure which quote I want to do, so I'm going to go with the funny one first. He said, "I do not think that radio waves I have discovered will have any practical application." So,
He was a little off base on that one.
oops. But the one that I like the most is that he says one cannot escape the feeling that these mathematical formulas have an independent existence and an intelligence of their own, and that they are wiser than we are, wiser even than their discoverers. So when you sit there and you struggle as a new guy who's just getting into this, who's just finding out that you can change antennas and get a wildly different solution, for your whatever problem you're trying to solve, keep in mind that the guys who actually came up with the theory and then proved the theory still didn't understand it the way you think you might want it. You might want to understand it. So you can have people who claim to be experts, but when we talk about radio, even the people who proved it, who won Nobel Prizes or would win Nobel Prizes if they had them back then, for these type of discoveries, still to their dying day, never understood exactly what we're talking about, what we're dealing with. I mean, there is just fascinating things. So if you feel overwhelmed, if you feel like you can't keep up, join the club. The people who've been doing it for 30 years, the people who did all the physics and all the math, they still don't get it. So yeah, you just joined a bigger club. You just don't know it yet. The other the other thing that I will tell you is, and I alluded to this earlier, you are going to make mistakes. You are going to screw this up. There is a reason why there's a whole group of people called ham radio operators or amateur radio operators. An amateur radio operator is simply someone who likes to play with RF. There's an entire community, there's an entire group that dedicate themselves to doing nothing but playing with the stuff and making mistakes and screwing it up. So just know that you're going to screw it up. You're going to make mistakes. However, you are not by yourself. You are simply joining the millions and millions of people. And when you think about, I mean, ham radio has been around for about 100 years now. Marconi came up with the radio, an actual radio wave that you were using voice on 130, 150 years ago. You're joining the millions and millions of people who have been doing this and are still fascinated and are still learning today. I still make mistakes. I still change things. 2 years ago, or no, a year ago, I got into an argument with a guy about power spectral density and how you calculate that. And it has to do with, sort of the antennas, and there's and it's dB math. And we spent an hour working through all the math until we could figure out what it was. And that was less than 365 days ago that I was having these conversations. People look at me and they go, "Jim, you're an antenna expert." And I'm like, "Oh, no, no, no. I know enough to be dangerous and I know enough to play, but I still make mistakes. I mean, 2 weeks ago, I was in an argument with a guy for half a day. And it wasn't an argument, it was a learning experience for me as I learned more and more about these electromagnetic waves and how they act, how they react. So don't be afraid to make mistakes. Don't be afraid to reach out for help. Don't be afraid to ask people, because I guarantee you're not the first. You're not the first one that's ever had this thought. You're now part of a club of the millions and millions of people that have been doing this for over 100 years. And we are still learning to this day about how these things work, because they seem to have this consciousness level. Electromagnetic and RF waves have this consciousness level that's even exceeds our own. And as you learn more about it, as you play more with it, as you see some of the natural phenomenon, the natural things that happen. We were talking about, the Tacoma Narrows Bridge that collapsed in 1960 because the harmonics of the wave and the wind matched, and the bridge just collapsed right after they built it. And if you've never watched that video, just go Google Galloping Gertie, and
Galloping Gertie.
you will
I'll put a
see
link to that in the show notes.
you'll see a fun video of what harmonics can do. And so it's like harmonics, these waves, and Tesla has an earthquake machine. It came up, and Mythbusters did an entire episode, and Mythbusters was like, "We want to stop now because we're getting to a point where the harmonics of these waves are kind of scaring us a little bit." And so you're just joining a club. So I will guarantee You will make mistakes. I guarantee you that you can learn from those mistakes. Whether you do or not is up to you. But don't be afraid of it, because yes, it is going to happen, but that's how you learn. And in RF, it's almost the only way you learn. And that's, again, amateur radio is all about failing, but trying again.
Jim, thank you so much, man. We have covered so many different areas. This has been awesome.
And we haven't even really, I mean, we went 2 miles wide and like a millimeter deep.
I know. Well, we're gonna have you back, and we'll touch on some more stuff, and it'll be a lot more fun. So
Yeah.
only next time we'll see if we can drink at the same time and see what happens.
Oh, no. Scott.
That could be bad. Maybe we won't record that one.
Well, that's why you go to conferences, so we can sit around and drink and tell war stories.
That's true.
And they're not recorded.
Oh my goodness. Well, that has been another great episode here at the Industrial Wi-Fi Shop. Thank you everybody for sticking around. Jim, thanks for coming and hanging out and talking with us. I hope everyone has a great day.
Thanks, everybody.
Thanks for listening, everybody, and we hope you join us on our next episode of the Industrial Wi-Fi Shop.